We're going to analyze these IR spectra for specific functional groups. We're not going to solve these spectra because we would need more information than what we have here, but we can look on the spectra for indicative absorbances that describe certain functional groups. So let's look at the spectrum labeled A. As we read in the text, we can divide this spectrum into approximately 4 regions, and you can do that with your pen on any spectra that you want to analyze. This first region, from about 2700 on to 4000 wave numbers, are any bonds from heteroatoms to H. So CH bonds, OH bonds, and NH bonds will appear here in this large region at the left end of the spectrum. The second region that we want to remember to analyze is the region at 2300 to 2100. That's a very narrow region. I often forget about it. But this is the region where we might find triple bonds, CC triple bonds, CN triple bonds, and they would be up here. And they're not very intense, so they'd be approximately, let's see if I can draw something. They might be approximately that long. And so we don't want to forget to look in that region because that's a very important bond and it tells us a lot of information about our molecule. We don't have that in this case. I'm going to erase this blue line. The next region is also a very important diagnostic region. It spans from about 1600 to about 1850. And typically we see large, strongly absorbing peaks in this region, and we have one in this spectrum right here. You can see that this peak has about a 20% transmittance, so it's absorbing a lot of the energy at that wave number, which is approximately 1750 or so. So we have our first interesting peak here, and this is from double bonds, CC, CN, or CO double bonds. And in this case, because it's so strongly absorbing, this is a CO double bond. We would see a smaller, shorter peak for a CC and a medium peak for a CN double bond. So I know from experience, and eventually you will know from experience, that this peak that we've identified with the blue labeling is a CO double bond. We can go back to the bonds to H in this case and look a little more carefully at that. Remember that we talked about, the textbook said, draw a line at 3000, and anything on the left side of that line is a CH on an sp2 type carbon. Anything on this upwards above 3000, I like to say, below 3000, so around 2950 or so, is a CH on an sp3 carbon. So that gives us some information as well. And we can tell if there are alkenes present, or at least we can see if certain alkenes are present. There are no alkenes present in this spectrum. Indeed, the only interesting peak is this peak at about 1750. So we know that our molecule has a carbonyl of some sort in it. That's all we're going to do with this spectrum. We've identified that there is a carbonyl. So let's look at spectrum B. We're going to draw the same lines again. I want a line at about 2800. That's our bonds to H. I want a line at about 3000. That distinguishes the hybridization of the carbon attached to the H. And again, you can see there are no sp2 CHs, so I don't have any alkenes in this example. I can look in the triple bond region. Again, that's 21 to 23. We see this little tiny peak. I'm not going to worry about that, so we're going to say there are no triple bonds in this compound that's creating this spectrum. And then again, 1600 to 1850. We've got this peak. Without any more information, I'm not going to draw any conclusions from that, so I'm going to ignore that peak for now as well. The interesting feature of this spectrum is this hump-shaped region, and you'll see that it has sort of two smaller peaks on it. When I learned about this, I was taught it's sort of like a Bactrian camel, right? It has two humps. And so a large hump here, like I'm trying to draw with the wrong color, is generally indicative of hydrogen bonding. And that can come, of course, from OH or NH bonds. And OH bonds will be much more intense. This hump that I've drawn only stretches to about 50% of transmittance, and so I think we probably have NH bonds. And because there's two humps, that equals, we have an NH2 group. Each of the hydrogens can essentially stretch or bend in different ways, and that gets us this two different intensities of two different wave numbers of absorbances, and that is what causes the two humps. If we had NH with two R groups instead of one R group, like I told you we had before, we'd expect only one hump because there's only one NH bond. So we don't have that. We have an NH2 group. So I'm going to just put that somewhere here. So I know that my molecule has NH2. And that's really the only conclusion I'm going to draw from B, because there's nothing else of interest on this spectrum. There's no triple bonds, no double bonds. And again, we're going to basically ignore just about everything that's in the 1500 and lower region. That's not going to be useful to us in this class. Go back one slide. You can see how, if I erase my scribbles here, this peak at around 3300 is much less. So let's move on to spectrum C. Again, I can draw some lines. Remember the 3000 diagnostic line, the 2800 tells me anything above here is a bond to H. In this case, I again see no sp2 carbons because there's nothing right up here. And then I need to look for triple bonds in the 21 to 23 region. That's right there, there's nothing there. 16 to 1850, again for double bonds, again nothing there at all. So I'm going to focus my attention on this interesting, large, broad, highly absorbing hump right at around 3350. And so you can see how that one, if we compare that to spectrum B, then the one that I circled in green on spectrum C. So this tells me that this peak here is an OH group. So I probably have alcohol on my molecule somewhere, and that's really the only interesting thing here for C, so that's all I can conclude for C. If I were to combine this OH group with a very intense peak, like I see here at 1750 that I drew in with green, I might conclude that I have a carboxylic acid, but that is not the case here. I don't have that, so all I can conclude from C is that we have an OH group. Let's look at D. Again, no sp2 hybridized carbons attached to hydrogens, really nothing of interest in that XH region. There are no triple bonds here. There are no double bonds here. So in fact, there's really nothing of interest at all, and that's a strong indication that we might have some alkane that's very boring. And you can see here I drew pentane. It has no triple bonds, it has no double bonds, it has no alkenes that are attached to hydrogen. It really only has saturated CH bonds. So for D, this is probably a pretty good guess as to what we're looking at. Got one more here, spectrum E. Let's draw our lines again, 3000. Now we can see that there is something just above 3000, and that is indicative of an sp2 CH bond. So that tells me there's some sort of alkenes here. Again, looking at 23 to 2100, there's nothing here. Looking at 1850 to 1600, this peak actually does appear in that region, and that is a very low intensity peak, so it's not going to have a strong change in dipole moment. So that most likely is a CC bond, and I can couple that with the information I had from the 3100 region, telling me there probably was some sp2 carbons here. So spectrum E probably is some version of an alkene, and we don't have any more information that we can use to predict that, so one pentene is as good a guess as any in this case. But that's the information we can get from spectrum E, that there is an H attached to an alkene, and I do have an alkene here at around 1650 or 1550 or so. So another very useful feature of IR spectroscopy is that we can analyze the starting material and analyze the product of certain reactions, and we're able to establish that indeed the reaction occurred. So this is one way that we can say, yes, we made product. So let's look at these reactions. We'll complete them. They're all review reactions, so we know that the hydrogen and palladium added to an alkene gives us this alkane. Again, we would expect something at around 30-50 wave numbers because we have the H's here. And we'd expect maybe something at around 1550 or so because we'd have the alkene. And here we'd expect nothing. Be a very boring spectrum like we saw for D. If we look at this reaction here, we have an alkyl bromide. We're reacting that with NaOH, strong base, strong nucleophile in water solvent, the conjugate acid of NaOH. This is a primary carbon. There is no beta hydrogen, so really the only thing the OH can do is a substitution. So we're going to make benzyl alcohol, and that's pretty easy to follow. Here we would expect something 3300 and very intense and very broad. And we would not expect that on our starting material because there is no OH group. So we can analyze this outcome by looking for the presence or absence of the OH. All right, in this reaction, we're adding methyl Grignard to a ketone. And we're simply going to end up with a tertiary alcohol. And that's going to look like this. And again, we can watch this, 1700 wave numbers or so. We'll see a nice intense peak. And then right here, we'll see a very broad, intense absorbance at around 3300. When we would not have the 1700 in the product, we would not have the broad absorbance at 3300 in our starting material. And in this reaction, we're going to take another ketone, react it with sodium borohydride to get an alcohol. So we're going to reduce the ketone now to an alcohol, and I would say we would expect the same outcome as we got over here. We start with 1700 absorbance, very strong, very intense. We lose that absorbance and we gain an alcohol absorbance at around 3300. Again, very intense, but also very broad. And the last one, chromic acid plus the alcohol. We know that that will produce a carboxylic acid. And so the difference now is that right here we had the alcohol absorbance again, basically the same 3300 broad hump. Here we'd have an OH absorbance, but we'd also have a carbonyl present as well. So we'd be able to distinguish between these two by the presence of the carbonyl absorbance.